So today we're going to do section 10.3, and section 10.3 is going to be about using chords in circles. So just as a reminder, a chord is anything on a circle that goes from one edge to the other edge, just like that. So that's a chord. This yellow line is a chord. It's also going to be our diameter. Remember, the diameter goes through the center of the circle, and that could be called like circle C. And we could have another chord that goes just like this. So chords can do all sorts of fun different things. And we're going to get today started off with a couple of theorems. By a couple, I mean three. And this first theorem we're going to call theorem 10.6. It is also known as the congruent corresponding chords theorem. And instead of writing out the theorems like we have been with all these different words and whatnot, I feel like it's better, especially in this format, to just give a picture, tell you what it's going to be about, and move on. So I'm going to draw a circle real quick that's going to represent our example for this theorem. And we're going to draw two chords. And our first chord is going to be called chord AB, and our second chord is going to be called chord C, D. And these two chords are going to be congruent. And so what this is saying is that if these are congruent, those two chords, then their corresponding arcs are also congruent. So if, and actually it's an if and only if, so this works both ways. So if we have arc AB, so this arc right here, is congruent to arc CD, so this arc right here, which that is given by the picture, if and only if chord AB, so now this is the segment, is congruent to chord CD. And I just realized that, oops, definitely meant to do that. I'm going to make those just good straight lines on top of there to not confuse it with the arc symbol. So that's a congruent corresponding chord theorem. If two chords are congruent, then the corresponding arcs are congruent. And if two arcs are congruent, then the two corresponding chords are congruent. Moving right along, we're going to do theorem 10.7 immediately following that. And theorem 10.7 is going to be the perpendicular chord. I don't know where this circle came from, but that needs to go away. The perpendicular chord bisector theorem. And the perpendicular chord bisector theorem is if a diameter of a circle is perpendicular to a chord, then the diameter will bisect the chord and its arc. So if we have a circle here, and then we're going to draw in the diameter of this circle, just like so. And so to be the diameter, it has to go through the center of the circle. And let's call this diameter EG. Now let's say we have a chord that runs perpendicularly to this diameter. So those intersect at a perpendicular angle. And we're going to call that guy FD. So what this is saying is that if that chord is perpendicular to the diameter, then this left side is, or the top side is congruent to the bottom side, and this top arc is congruent to this bottom arc. And we'll say they intersect here at H. So this is going to say the following. If EG, which is our diameter, and EG is perpendicular to some chord, DF, then HD, so that bottom part of the chord, is congruent to HF, the top part of the chord, and GD, the arc GD, is congruent to the arc GF. So that's what our perpendicular chord bisector theorem is stating. And then finally we have theorem 10.8, which is going to state the following. It's the perpendicular chord bisector converse. And now the converse normally is when you say then if. So we would say if this yellow chord is bisected, then the arcs are congruent, then the following line must be diameter. So we'll draw that up real quick. So here is our circle. We have our diameter going across like so, and our chord going just like that. And all as we're given is that this is a right angle and those two segments are congruent. Might be helpful to draw in some more points there. So we got point P, we have S, we have Q, and we have T, we have R, and it says if QS is a perpendicular bisector of TR, then QS is a diameter. All right, so we're going to use these different theorems in a couple of examples real quick. Our first example is going to look like the following. We're given two circles. So there's circle P here on the left, and I'm gonna redraw the center of that circle there to be more in the center. So we have circle P and we also have circle Q. Circle P is going to have a radius right there, and circle Q is going to have a radius right there. And we're given that circle P is congruent to circle Q. And we learned last time if you have two congruent circles, then the radii must be congruent. Then we're also given a couple of chords. So this first chord is going to be right there. The second chord is going to be right there. We're going to label the one on the left GF, the one on the top JK, and we are given that GF is congruent to JK. We're also given the measure of arc JK is equal to 80 degrees. So this is at 80 degrees right down there, and we want to find the measure of arc. Oops, I put JK in the wrong spot. We'll just say that the measure of GF is 80 degrees, and we'll say let's find the measure of arc JK. Well, we're going to use the corresponding congruent chord theorem, which states that if two chords are congruent, then the corresponding arcs are congruent. And we know that these two chords are congruent given this statement right here, but our original theorem, they had to be in the same circle. Well, technically they are in the same circle because the two circles are also congruent. So you could kind of imagine taking circle Q and overlapping it over circle P, and that this chord would just be right here. So now that is chord J, K. And since those two chords are congruent, then the measure of arc JK must be equal to 80 degrees. So it's a pretty straightforward example to get started with. We're going to go ahead and do something a little bit more complex now. So I'll let you look at that for just a second. All right. We're going to have a circle over here. Oops, let's get my black pen out. Here's our circle. We're going to have a chord running from here to here. That's going to be called chord HK. And we're going to have a diameter running across right here, intersects through the circle M, intersects that chord at N. We have J and L as its endpoints, and it also intersects at a 90-degree angle. And then we're given some measurements. Arc JH is 11x degrees. Arc JK is 70 plus x degrees. And the length of NK is equal to 7. So we're going to have two goals in this example. We're first, A, going to find HK, and then B, we are going to find the measure of arc HK. So first we need to find the length of HK, which is this chord right here. Might want to do a better color than red. So we're going to do that in yellow. And we know that if a diameter is perpendicular to a chord, then it bisects that chord. And so each side of those is congruent, so we just have to add them up. So HK is going to equal 2 times the length of NK, or 2 times 7. And so HK is going to equal 14. We also know that since this diameter is perpendicular to this chord, it not only creates two perpendicular segments along the chord, it also cuts this arc perfectly in half. And so we know that the measure of HJ is congruent or equal to the measure of JK. And we have to find this entire arc all the way across. So let's first solve for x, and we'll do that by setting 11x equal to 70 minus x. We will go ahead and add our x. Oops, what am I doing here? Oh, I made a mistake. See, this is a plus sign right here, and I wrote down a minus, so we need to put a plus there. So we got 10x is equal to 7, d. Divide by 10, and we get x is equal to 7. Now we're going to go ahead and plug 7 back in to find the measure of HJ, which is equal to 11 times 7, or 77. And then we know that the measure of HK is going to equal 2 times the measure of HJ, which is 77, which is going to equal 154. Sorry, 154 degrees. I really like these examples with these circles. I really feel like we're getting back to the basics of geometry that we were doing at the beginning of the year. So that really makes me happy. All right, so moving right along, we're going to have another theorem. It's going to be our last theorem of the day. Theorem 10.9. And theorem 10.9 is going to be the equidistant distance theorem. I'm almost confident that this is not called the equidistant distant theorem. I'm sure I wrote it down wrong, but that's what's in my notes, so we're going to roll with it. And it says that two chords are congruent if and only if they're equidistant from the center of the circle. So if we draw our circle here, we draw a couple of chords in. So there's going to be a chord, here's going to be a chord, and then the center of our circle is going to be right here. And remember, equidistant means that the line perpendicular to our center is the same distance. So if we draw a segment from this center to there and this segment to there, and they're both perpendicular, then these two chords are going to be congruent. So what this says is the following. AB, so that chord on the left, is congruent to CD, the chord on the right, if and only if EF is congruent to EG. So we will put those in right there. So they're the same distance from the center, so they must be congruent. All right, so now this is all accumulated up to our big final example. So why don't we do our big final example? We're going to draw a big circle, not in red. There we go. And we're going to have the center of the circle right here going to be called circle C. And circle C is going to have a lot happening with it, so I might just need to take a second to draw that all. And of course, when I need to draw a bunch, my pen decides to be finicky, so. Okay, do I have everything of interest? No, I don't. We're still going here. Alright, so there is definitely a mistake in my drawing that I'm going to need to fix because that blue line is supposed to intersect that chord down there at a 90-degree angle. So let's fix that. Sometimes drawing these big drawings is very difficult. So we'll say that right there. And so that intersects at a right angle. Our top half is completely screwed up now because of the premise of the problem. So we'll get rid of all of that, redraw the top half. Guess I should have drawn that red line first, huh? W didn't move too much. Got U right there, and we got R right there. So here's our problem. And then we also have a green line right here, here to here, and that is going to be our radius. Okay, big problem, lot going on in this circle. All right, we're given the following pieces of information. QR is equal to ST, which is equal to 16. Oops, and sorry, ST is right down here. So those two chords are congruent. I know they don't look congruent. Please roll with it. These things are difficult to draw. CU is equal to 2x. So we can go ahead and fill that in right there. That's our 2x. And CV, I don't know where that y came from. CV is equal to that 5x minus 9. Our goal is to find the radius of the circle. All right, so first thing we need to do is we need to find this length right here, CU, because if you notice, we have a right triangle right here. And that that green leg is the hypotenuse of that right triangle. So eventually we're going to use the Pythagorean theorem to solve this. All right, so the first thing we need to do is find the length of CU. All right, and notice that these two chords are perpendicular right here. They're also equal to one another. So CU must be equal to CV. So that's that 2x is equal to the 5x minus 9, or 3x is equal to a positive 9, or x is equal to 3. And substituting in, we can get that CU is equal to 2x, which is 3, or 6. So why don't we replace this here with a 6? Now, since this is perpendicular to this chord, and this is also a radius, we know that any radius or diameter that is perpendicular to a chord is going to bisect that chord. So we know that this total length of 16 is going to get cut in half, so this other side, QU, is equal to 8. And so now I'm going to redraw my right triangle here. So our radius is right here, and we got C right here, U right here, Q right here. This guy is equal to 6, this guy is equal to 8. And now to find our radius, let's use the Pythagorean theorem. So our radius squared is going to equal 6 squared plus 8 squared, or our big R squared is going to equal 100. Take the square root of both sides and we get R is equal to 10.